So, good morning. Third lecture about software architecture. You have the slides and some extra references also in the course homepage. And you should be able to follow the lecture quite easily using that material. This material is extracurricular, so it won't be on the exam, but it can be a good read anyway. That being said, we also have the deadline for the workshop today at noon. So if you have not already used the submission form, please do so. And you need to log in first, so you click there and you supply your usual username and password. And the link should be live, and if you click that one, you will come to a form, and note the nautical theme. Spent a good deal of time fixing that, but you just submit here, and it's sufficient to submit once per group. So you have the contact person first, that's mandatory, and then you can add the second and third member of the group, also the URL to your work and what language you use. So if you use Swedish, you select Swedish, or otherwise you select English. So that should be it. A fair amount of you have already done this, so it should not be a problem. But if you have not done so, please do as soon as possible, because the form will close at 12. And then I will start compiling lists for peer reviews, and you should be notified about peer reviewing this afternoon. So check the homepage this afternoon, and you should have instructions on the peer reviews. So I hope the workshop went smoothly. I met some of you here in Kalmar and online also, and it seemed to work out. So this workshop was, as I said, quite small, so maybe you did not need that much time to do it. I can once more mention that the second workshop is by far the largest one, so you can start on it right away. And for example, you can see that you need to be able to save and load a member register here, so you could start up by doing that. Functions. Some file handling is always good to have a good grasp on. You could use XML, for example, a good file format for this kind of stuff. But you are free to select whatever you want. This requirement, the strict model view separation, is something that we will talk about today. So if you don't know what that means, you will do so after this lecture, hopefully at least. So today we are leaving the reality land of domain modeling, of analysis, and start talking about software. And to be able to have some kind of frame for our project, we will talk a little bit about software architecture. In the following lectures, I think at least 3 lectures are dedicated to more or less software architecture and learning a little bit more about that. So, onwards. And today we will talk more specifically about the model view separation principle, and we will also hopefully do some coding, at least in the second half of the lecture. And I hope maybe if there is time, we could also do some questions and answers maybe for the first workshop if you have some interesting issues to take a look at. So, software architecture is a fairly large topic. We will not dwell that deep into it. You can have entire courses in software architecture, of course. We will focus on the areas that are important for the programming part, you could say. But basically, the software architecture is the high-level structure of a software system. And why do you need a high-level structure? Well, as some of you may have noticed, if you have done a project, maybe on your own, I know you had some individual projects here in Kalmar at least. And while you may be a good coder, you have a really good understanding of how to program and how to implement, sometimes that is not really enough. Because you make a lot of decisions, maybe early on in the project, that you kind of have to live with. And when you implement, you also make decisions all the time. And some of you may have got the experience that, well, after a while you implemented, stuff kind of like became harder and harder as you progressed. Maybe you added a feature, but 2 other features were broken when you added that one. Or changing a feature was not really that easy because it was dependent on so many other things that also needed to change. So having a good low-level design and implementation is not enough, especially not in larger projects where maybe several people need to synchronize and be able to put their work together. And as I said, you have these early decisions that you make that can have a large impact on your project. For example, it's very easy to just make technical decisions really early on. Oh, I want to work with this framework. I want to work with this technology. We should make a web-based system. So one point in software architecture is to shed light on these early decisions and actually try to understand the impact they have, and not just go with the latest technology or the safest technology or the old technology, but actually trying to decide and make a more informed decision about what we are trying to do and what is best for us in this situation. So, software architecture is very much about qualities. It's not so much about functionality. You can implement most functionality in every kind of architectural style you could imagine, but the quality of that implementation will be different depending on the style of the architecture. And with qualities, we have these things like performance, security, reusability, changeability, maintainability, all these ilities you can imagine. For example, you maybe need to have good usability in your system. So you decide you make a web-based system because users are used to the web paradigm in applications nowadays. A familiar user experience and user interface provides good usability. At the same time, you maybe have high security requirements. So the decision to make a web-based system is good for usability, but probably not that good for security. Because web-based systems are, well, they are on the internet, and that's an open network. Then you need to add encryption. You need to add a lot of security configurations to your servers. You need to keep your servers updated. So by doing that decision, you kind of like affect the security and the effort you need to spend on security by doing a web-based system. So the idea of software architecture is to take these decisions and find a good balance. Find the trade-offs you are willing to make. Is the security so important that we need to sacrifice some usability and make something more custom maybe. Maybe we can't have this on an open network. We need to have a private network of some kind. Or maybe the usability is that important that we can live with the extra effort that we need to spend on security in the internet domain instead. In the unified process, this is part of the elaboration phase, the goal of the elaboration phase, and the idea is that you should think about these qualities, these early decisions as early as possible to get rid of as much risk as possible in your project. Because changing from one architectural style or one of these decisions late in the project can have a large impact. Maybe you need to throw everything away that you have done and just start from scratch. Or you need to spend a lot of time figuring out how to change your system. So the idea of software architecture is to facilitate communication. So team stakeholders and project stakeholders can discuss these qualities, discuss early decisions, and know what will be the impact of these decisions and qualities. We'll facilitate evolution of your system so that you can continue to evolve it, especially important in today's more agile and continuous delivery approaches to software development. Facilitate reuse of components in your systems that you can use in other situations and other projects. And of course, risk management, as I said. I think that Jesper has done an excellent suite of lectures in some of your first year courses about software architecture. So I will also link these, I think, in my webpage, so you can listen to his discussion more about software architecture also. So, as software architecture is a topic that requires knowledge in several different areas, you often see these kind of views that you should be thinking about when doing software architecture. And a classical approach is the 4+1 view. There are probably more views also. I think in the book he mentions the 4+n views. So the idea about views is to look at the architecture from one kind of viewpoint. Because mixing everything in one single viewpoint often just becomes very messy. And it becomes hard to know what you're actually talking about when you are discussing this diagram. So often you kind of like see this, you have a cloud that says internet, and you have an arrow from the cloud to the database, and you have some client also. That is a typical, some kind of a high-level architectural diagram. But you never really know when looking at the diagram like that, are you discussing hardware? Is it the client's hardware and the database server that we are discussing? Or are we discussing network protocols? Are we discussing where processes execute? And so on and so forth. So, the classical example is the 4+1 view then. And here we have 4 views that are held together by a 5th one. So to start off with maybe the thing that we will be looking most into, the logical view. This is where you structure your application using class diagrams, packages, namespaces. You work with these sequence diagrams also to show how the objects are collaborating to fulfill some requirements. So basically this is what we will be doing a lot of in the course. In the development view, you structure the components of the system, and in unified process the component is a very broad subject. It's basically anything that is a physical file. So a source code file is in some respects a component in unified process. So this means that this tells the developers how to structure their code. Where should files go? Where should we put this? Also, what kinds of other components are we dependent upon? For example, could be external APIs, databases, and stuff like that. And the goal of this view is to try to create reusable components so that you can package the components that you actually develop in the logical view into something that you can structure and layer. Then we have the process view. Here we show the different components, high-level components, where they are executing. So this component is supposed to run on this process, the database server process, for example. And this is running in the client process, the web browser, for example. And lastly, we have the physical view, and this is about hardware, network standards. How are these things to actually be wired together? What kind of performance do we need on our database servers? How should things scale in the hardware? And things like that. And to tie things together, you have the scenario view. And the scenario view is actually just a select few requirements that we feel are representative to show the architecture. So by using these requirements, we show that, okay, for example, if you have the login scenario, okay, we show that how the login scenario works in the logical view, in the development view, in the process view, and in the physical view, so that we can understand the software architecture based on our requirements. And the idea is, of course, to select a good representation of requirements for the scenario view so that you don't miss anything in the architecture. And this is something that is maybe not always that easy to select the architecturally significant requirements. In this course, basically, we will stay in the logical view. We will be doing class diagrams and stuff like that. We will use the development view a little bit, maybe, to at least show how you can package your code so you can maybe reuse it more easily. We will not talk at all about the process and physical views or the scenario view. And of course, after we have kind of like done this architectural design, we will delve more into the more detailed design. So then, the logical architecture. It's a large-scale organization of classes into packages. In Java, you even have the keyword package. I think in C#, the implementation of a package would be a namespace. So it's quite straightforward. So the idea is to look at the design and find logical groupings of classes that collaborate closely. So if we could maybe do some writing on the smartboard. So if we look at our design, we maybe have some classes up here. And they are kind of like working tightly together. And we have another bunch of classes. That are also working quite tightly together. And a third bunch of classes. Something like that, maybe. And between these classes, you have some collaboration. But it's actually not that much. So looking at your design, you can find maybe clusters like this. So you have the blue ones and the green ones and the red ones, and they collaborate more closely. They do kind of like the same thing within the same area of responsibility, and by doing so they are tightly coupled. So the idea is then to find these clusters and try to encapsulate them even further. So by doing this, maybe we say that, well, you can't really just call a function on an object that from a class that resides in here. You need to create an interface first, and this is what you can actually call. So we try to hide this stuff that is inside this ball, so to speak, and we define rules on how we can access stuff from in there. So, well, we can decide that, well, you can't really create an object like that just and use it. You need to create this interface, and maybe you need to do some extra work here, but we try to keep all the dependencies focused on this interface instead. So we try to define these clusters, try to define how to make good collaborations between these clusters and what is not allowed also. So yeah, we encapsulate further and we define the valid dependencies. And the problem is how to do this, because you can't really look at do a detailed design over the whole system and find these groups from the onset. We need to kind of like do this before we do the detailed design. So how should we do this then? Well, you can of course use experience, and that is what most people use. Well, I have done 5 systems like this, and it's a good idea to kind of like have these groupings and try to do this. And oh, the last project did not work out really well, so we should try to do some changes or whatnot in the overall architecture. However, there are also guidelines and principles to follow. And this is good because other people have done systems for quite a few years, and it would be bad if we did not learn from their experiences also. And this is something that we can find in for example, guidelines, principles, or patterns. And also the book is kind of like named Applying UML and Patterns. So this is something that we will do a lot in this course. So a software pattern then. It is actually nothing more or less than a named abstract problem and solution. So you have a situation that is problematic. This is described in a generic way. You have a solution to that problem that is also described in a generic way. So you have the motivation, why you should use this. You have the structure, that is the solution. You have consequences, what will happen when you do so. Often things can be good in one way but bad in another, so you need to find what is best for you. And you often have examples. So This is something that is described in books, for example, in patterns. These abstract problems, the situations that you may face, but they are described in a generic way, so they won't really say something exactly about your project, but your problem. So this is where you live. You live in the world of specific problems because you are in a project right now and you are supposed to develop something and you have this problem that you cannot figure out how to solve. So you need to find the abstract problem that fits your specific problem. Oh, wrong. And when you have done so, you can take a look at the abstract solution. And you can develop this into a specific solution. And basically this is the work you do. Using your knowledge about patterns, books, whatnot, you can take your specific problem and find one or several abstract problems that are suitable. You look in the book and look at the consequences. You select a solution that seems to be good for you. You look at the abstract solution, the structure of this pattern and what you're supposed to do and how things are supposed to work. And you, of course, need to adapt this to your specific situation, your specific implementation language, your specific design, and your specific language. And hopefully you have made the right choice and everything will work out as prescribed by the pattern. So this is actually what we will be doing a lot in this course. We will take a look at specific problems. We will try to find a pattern that matches. We'll take a look at this pattern and we will then implement the solution using the pattern. And of course, knowing a lot of patterns and knowing at least in what direction to search for patterns is something that comes with a little bit experience, and this course can only give you kind of like the first stepping stones. But patterns is a good way of encoding knowledge in software development, and it has become standard almost to do this. So knowing about patterns and what they should provide is something that is a valuable skill. I have a question here in the chat. Is scenario view like use cases? Yes, the name scenario view comes from the scenarios in use cases. A scenario in use case is one specific path through the use case. You often have the main success scenario, for example. I don't know really how much use cases you have been writing, but that is the idea that you take a specific way through the use case. Could be as something that goes wrong also, but some specific requirement, and you use this as almost like a tutorial or something like that, and you show these different views in the light of this requirement. So, patterns. Principles and guidelines work in quite the same way, but they are not maybe as specific as patterns. Patterns can be very, very down to earth and quite specific, especially the design patterns we will take a look at later on. And as you move up to more abstract level, you have principles and guidelines also. So towards the end of the course, I think the last lecture, we will take a look at the some principles, and you will see how the patterns that we have been using relate to these principles, and hopefully that will make things a little bit clearer also. So, and as I said, the structure of a pattern is often like this: that you have the examples, for example, towards the end of the pattern description, so you can see how it can be implemented in different languages, for example. And often pattern books are geared towards some kind of language. You have Java patterns for this and that domain. And one book that is on the recommended reading list is this, Pattern-Oriented Software Architecture, especially if you're interested in software architecture, and especially logical and development view of things. You can take a look at this book. It describes some of the usual and commonly found patterns in software architecture. It's a really nice book. One thing also to remember about patterns is you can't really find a new pattern, because all patterns are so to speak already in software that has been developed. So it is very much encoded experience from successful development projects. So you can't really invent a new pattern, because they don't exist. You don't invent patterns. You find patterns maybe in several different softwares that you have been developing or you have been studying. So you cannot invent a new pattern. You can find one, possibly. There are also anti-patterns that are descriptions of what not to do. And these can, of course, also be good, because sometimes you kind of like make things worse, and you should know how people beforehand have made things worse to avoid their pitfalls also. So, as I said, the first principle we will take a look at, and this is also a requirement for the second workshop, is to follow the model view separation principle. And the idea of the model view separation principle is to separate business logic from user interface and presentation. And this is, of course, a pattern or a principle that is used in interactive software, because you need to have a user interface to be able to do it. So it's mainly used in softwares that are used by humans. And the idea is that, well, user interface technology and presentation often change quite rapidly, often more rapidly than actually domain and business rules change. You know, of course, domain and business rules can also change, and businesses develop, but technology for user interfaces and presentation seems to change faster. So by keeping these two separate, we can evolve these two parts separately. Also, doing a good user interface requires quite a lot of intimate knowledge about user interface APIs. So you often need to know be a technical expert to make a good user interface, because you need to use some kind of framework, some kind of components, tools, etc. to make this a really good experience for the user. And this is quite another thing to be a good domain and business rule expert, for example in banking or insurance or what it might be. So it's a good thing to be able to utilize experts in each of the areas in a project. So if you have people that are experts in user interface technology, you should of course let them work on something they enjoy and are experts in, and not need maybe to worry that much about detailed domain and business rules, and vice versa, of course. So, an example. We're doing a math application, and we are concerned with circles. So we create a circle class in our design. And to be able to fulfill the requirements, we need a radius. So that we can compute area. So we have some data in the class, the radius of a circle. We can compute the area using this radius. There are possibly also other math functions that we need. Circumference, for example, but I won't spell that one out. So this is basically our domain and business rules. We do math application, computing, circles, area, and stuff like that. However, we also need a user interface. And we need an interactive user interface so that users can look at their circles on the screen. They can maybe move them. They can change the size of them. They can give them different colors. They know which circle they have selected, so they know the area, what circle's area is displayed. So what kind of data do we need to add to our circle class to facilitate these kinds of requirements? We need the radius because we need to know how big the circle is to draw it on the screen. Do we need to know anything else? Yeah, we have the getArea function, or what we would like to call it. To be able to draw the circle on the screen, we need the radius, but we also need the position. Exactly. So we add an attribute. All right, we can now draw different circles with different sizes in different places on the screen. Yeah, exactly, the center position. Anything else? Color could be a good idea. Of course, we need to have different colors. Anything else? Maybe we also need to know if the circle is selected. So we add an attribute for that. And we're kind of like out of room now. But we could imagine that we have different colors. Maybe we have a fill color and a line color and an is a selected color. And maybe we have different thicknesses of the line. We have a switch if we should show the center point or not. Should we show the radius as a line? Well, we can imagine all these kinds of neat user interface attributes that we would like to have in our circle also. And basically we need to have some function here that, well, oh no, not that name. So we can draw the circle. And to be able to draw the circle, we need some screen. So something like that is then the final design of our circle. Everything works out beautifully, and we can calculate all the stuff we need, and we can also have a neat user interface for our circle. However, in our next project, we're not doing an interactive software, but we're doing a batch processing software instead. This batch processing software is, well, it's maybe supposed to take a bunch of circles and just compute a total area for all these circles. So we input some kind of like gigantic file or something like that with all this data. We would like to compute the total area and stuff like that, and just return a value to the user. So it's not really an interactive piece of software. We would not like to draw all these circles and stuff like that. But we know that, well, we did this really good circle class in our previous project, so we should reuse that because it's well tested and stuff like that. That's always a good thing. However, this won't be as easy as we thought, because we get all these extra stuff that we don't really need. We get all these attributes, and all these attributes are used maybe in this function, and this function has some kind of dependency on a user interface API to know how to draw the screen. So suddenly we need to include a whole new API in our small batch processing program. It has a dependency on a user interface that we don't actually need. And this may of course be fine and dandy, but we then also need to keep the batch processing program updated when you get updates to the user interface technology API. Then you need to kind of like recompile and redistribute this software, really just because something that it was dependent upon changed, and that's not a good thing. It just adds more and more complexity. So this is a small example of a mixed type that has not been developed with the model view separation principle in mind. Because we can see here that, well, you have the business rules. They operate on one attribute, and you have this draw that operates on a lot of other attributes, and we needed to add a lot of stuff that really did not have anything to do with the business rules, just to get things working. And also, maybe the worst thing was that we needed to add this screen, and we had a dependency here to this, and this is probably inside some API for user interfaces. So maybe it's just a simple put pixel or something like that, so that we can draw the circle. So you should of course not do this. You should try to keep it separate, so that we have our circle here. With the radius. And the operations that operate on this radius and that are actually the core of the business rule. And maybe you have some kind of interactive circle here. with all the positions and the draw operation. And this needs to have some kind of dependency on this, because it needs to have to access the radius to be able to draw the circle, and it has also dependency to the screen. But as you see, by doing this separation, you can more easily reuse this. You can have the math expert work on this. You can have the user interface expert work on that. You can even have several different kinds of interactive circles to draw in several kinds of ways, and you can have several developers working in parallel on these classes. So by doing this division of stuff into a model that encapsulates all the business rules, and a view that encapsulates user interface stuff, we gain a lot of good things. We gain reusability, we gain the ability to allocate experts to different parts of the code. Instead of one big circle class that becomes really, really complex, you have kind of like divided the problem into several subparts, and these can be distributed to different developers, and we have better scheduling and stuff like that. And we also have decoupled the business rules from user interface APIs and stuff like that to even further facilitate reuse. This is, of course, quite a simple example. In reality, well, things are always not that clear-cut. So we will take a look at a more complex example and do some coding. But I think we will do this after the break. So I think if there aren't any questions, we take 15 minutes of a break. All right, we take a break then.